Hi, today we're going to see another interesting video on the topic Hierarchical Navigable Small World Graphs. This is a very important algorithm which powers a lot of vector databases. So, if you are aware of the AI thingy which is going on, vector databases helps you to retrieve embeddings out of the embeddings out in the RAG implementation. So basically, it's just a database to store vector. Vectors are a group of, for simpler terms, it's just a collection of numbers, just collection of numbers. So you store this embedding in the vector database, and then when you query a new vector to it, it just retrieves something and gives you back. We'll see all of this and why this algorithm is very important and there are a lot of popular databases which still uses this algorithm, like Pinecone is very famous, but it uses hierarchical navigable small world in it, and then why it is effective, and then how this algorithm works and everything. Before understanding hierarchical navigable small world, we will split into smaller pieces and understand the smaller pieces, and eventually we'll combine it together. So the smallest pieces are Skiplist, navigable small world graphs, and then we'll have this hierarchical navigable small world graph. So first let's see what vector databases are, and then why these vector databases are like now people use this left and right center. You see company bringing up vector databases. Postgres has a Postgres vector database. There's Pinecone. There's one by Facebook which has been there for years. There's Neon. There's so many vector databases available in the market. Suppose there is this popular technique now people use called RAG. 1,1 is a 2D vector. 1,1,1 is a three-dimensional vector. Vectors is just a collection of numbers, and then you need to somehow represent this number in the database. How do you store it? You can't store it in the typical RDBMS SQL databases because it's just a bunch of numbers. You have like there are like thousands of dimensions. Let's consider three dimensions here, which we can visualize. More than three dimensions, it is very difficult to visualize. So we have 1, 2, 3, and then we have 4, 5, 6, we have 7, 8, 9, and so on. So we need to represent these numbers in our database so that we use this for some other purposes. So how do we first store these values? We can't use RDBMS because how do you store? It's just a bunch of tables here. How do you store these numbers efficiently? Or if you think about NoSQL, like on MongoDB, what is this structure means? You need some kind of an object notation to store it there. And then how easily it will be to retrieve. Like suppose you need this number, you need to find some relation between number. How it is even possible? All you can do is traverse and traverse and traverse, and you can't do much with that. So they came up with this vector databases. It just stores the data in the n-dimensional space. So what is the use of storing it in this form? First of all, the numbers in the vector itself has a lot of meaning to it and lot of information regarding some word here. So which we called as embedding here. So suppose we have an letter apple or letter A, we can represent this letter as form of an as embedding, which is nothing but a vector. So these embeddings helps you to recognize the letter as well as form some relations with some other data. Suppose you plot some value here and you plot something very closer to you. You can always retrieve data which is very similar, which are very closer to each other, which means that they are very similar. So that is the main idea behind this RAG application, where you just I'm just dumbing it down in very simple language, which we can see. I will explain it in some other video about how RAG works and everything. So you just take the vectors and then in RAG, suppose you have a 5 sentence. So you convert this into some vectors and then you dump it into this database. So when you search for the sixth sentence, you again convert into vector and then try, that is our query, and then we see what are the vectors nearby to this query, and then fetch all these data. These act as the context for the LLM models. So along with the query, we give these context which we retrieved from our vector database, so that the search is even the result which LLM gives is even more efficient. So this is all about vector databases. So now we have a lot of black boxes in it. So in assume this is a vector database, we say we just dump it in the vector database, which is straightforward. We have dumped data inside vector databases. Now when we have a newer query here, which is also some number, how do we retrieve information which are very similar to all these, which is very similar to the query? We have multiple algorithms to find all these similarities. Like there is like plethora of ways. Like example, there is an algorithm called localized sensitive hashing, and then there is another algorithm called disk ANN, and then there is memory ANN, and there are like a lot of techniques. And each technique has its own advantages and its own disadvantages. But one very popular technique to extract all these similar features out of the vector database is our hierarchical navigable small worlds. I think this introduction is clear enough. So we have storing some data in our vector databases, and then we need to find, when we give a query, we need to find the similarity to that query. And the one important algorithm to find similarity to this query is using hierarchical navigable small world graph algorithm. Let's see why should we even use an algorithm to do so. Suppose you are searching for a query queue, and there are like let's assume there is 4 vectors which is already present in our vector DB. So the most brute force way of doing it is just calculating similarities between this, that, and that, and then take the best out of the lot. Similarity in the sense we will bracket it under some measure. I will talk about what are these measures. There are different measures like Euclidean distance, cosine similarity, there is Hamming distance, there is Manhattan distance, and so on. These are like we'll keep it as a black box for this video. We are going to measure similarities between our query and the vectors with some method. And using that method, we are uniformly going to apply that method all over the place, and we will find similar points. So this is the brute force way of just checking with one after the other, and it takes O of 1 complexity. We need to find a way better than O of 1 complexity to do so. That's where this hierarchical navigable small world graph comes, which its overall time complexity is about of log n times. So it's just a logarithmic search. And this algorithm is inspired from this Skiplist data structure, where Skiplist is a method to efficiently search through an linked list. I will link a video in the description about Skiplist. It is a very beautiful video with very good animation of explaining Skiplist. But for this video, I'll just explain a little bit about Skiplist and move forward. Wanted to learn in depth about learn and understand about Skiplist, I will link the video in the description. This hierarchical navigable graph idea is inspired from the Skiplist, and it's being enhanced and then added some more layer to it. So let's see first what Skiplist is. So we know there is a data structure called linked list, where assume this is one linked list, the last layer. Don't see everything other than the last layer. Consider this last layer alone. Assume you have sorted the linked list also. So you have a sorted linked list. even though you have a sorted linked list, it is really it is not possible to uh, find the position of a number, or find whether the number exists or not directly, or through binary search and everything, because you don't know, uh, because all you have is the address of this first element, and then to find some element you just need to linearly traverse to it and then go find that element. So the time complexity it takes for search is big of n. So how can we efficiently do this? That's where this skip list comes in. So first we have this lowest layer L0, L1, L2, L3. Why I'm going into skip list is, so if you understand skip list very well, it's just an expansion of skip list, so that you can understand how hierarchical navigable small world works as well. So in L0, you have all the elements in the linked list. So first you have 7, 11, 13. These are all the elements in our linked list. This is our level 0. Then assume we have some kind of an function. Assume that we have some kind of a function to determine whether we can. So because how this works is, we are constructing from one level to another level, and then how do you select node for the other level is, it is very randomized. Some function, using that function you determine whether you can pick the number or not. It can be like literally any different function. But so for here, let's take, we have a coin. Coin is a function which has head and tail. So when you get head, you choose that value. If you get tail, you skip it. It is very simple. Similarly, there can be many different functions here. I have taken one function called coin tossing, which that function is helping me to get a randomized pick, whether I can pick or where I don't have to pick. So first I go to this 7 and I toss the coin and I get a head. So since I got a head, I pick this value in the layer 1. And then for 11, I got a tail, I haven't chosen it. And then 13, I got a head. 15, I got a head. You can see now from in level 0, you have all the elements. And then in level 1, you have a smaller subset of elements here. So again, in level 2, you do a coin pick for level 1 and say at 7 I do a coin toss and I get a head. So I've chosen it. And then for 13 and 15, I'm getting a tail, so I'm not choosing it. For 25, I've got a head, I've chosen it. For 53, I got a head, I've chosen it, and so on. And then you can always do another level, so on. And then you will have the next question: how many levels can I do? So assume in this level 3 also you get 2 heads. You get all heads. So you will have 11, 25, 53, which can keep going and going and going. But the ideal way of doing is to maintain the number of levels, which is equal to log of n, because we eventually wanted a logarithmic search here in the worst case scenario. So the worst case scenario, you can go from level 0, you can even stop at level 1, level 2 and so on. But the worst case scenario, we go at log of n times. So after this, now suppose you want to, okay, so now we have this level 0, level 1 and level 2. Now we want to search for a number. Let us say I want to search for 25. So first I start at this level. This is like this is a pointer before the starting pointer. Let's say it is minus infinity, this is plus infinity, some random pointer. So I want to search 25 here. So I just look for 25 and then there is no element. So I go a level down here at L2 and then I search for 7 and then the next element is 25. So since I got 25 here, I'm done with it. So you see, you haven't even searched n times here. You searched like 2 times, because n here is 3, 6, 9, about 10, about 9 or 10 elements. 1, 2, 3, 4, 5, 6, 7. So n is here 9 elements, but you have found your result in the second search itself. Let's take even a complex example. Suppose you want to search 11 here. So what you do is, at first there's nothing there, and then at this layer you start at 7 and you see 25 here, and you notice something. Since the array is sorted, you don't have to go beyond 25 because 11 will be between 7 and 25. So now our region will become from this to this. We have to search for 11 from this half row. This is nothing but our classic binary search here. So now again, our work at the level 2 is done because we don't have to proceed further. We haven't found the number. So at level 1, you see the first number is 7 and the next number is 13, and you notice that 11 should be between 7 and 13. So your work at level 1, layer 1 is also done, and then immediately you go to the lowest level and then try finding a number between this boundary, and then you eventually find it. Suppose you want to search for a number 12 here, you would have come to the last layer, but you wouldn't have found the 12 here, and you would try to go a layer below that, which is not available because the lowest layer is L0. So if you can't find a number at L0, then the number doesn't exist. So this is the basic idea between Skiplist. So initially we would have done n traversal here, n traversal to find the number. Now it has become a logarithmic traversal, which is nothing but this is some classic binary search here. Instead, now we instead of just compromising with time, we are compromising with memory by storing the additional info and additional layers. That's the difference. I hope Skiplist is clear, because based on Skiplist we have enhanced so based on Skiplist and navigable small world graphs, we've combined it together into an hierarchical navigable small worlds. So let's see what is navigable small world. So it's just a collection of elements, collection of vectors here. How it is, suppose we'll take one small example. We have a vector A, and then we have vector B, and then we have vector C, a vector D. So now we need to form some kind of an navigable graph here. Navigable graph is nothing but it is a bidirectional graph connecting between the elements, and we have we have enough proof that instead of searching directly, the searching through a navigable graph is more efficient, and it is possible to search in a logarithmic time. So searching through a navigable small world graph is polylogarithmic. That is, it comes approximately over log k to the power n. Some other day I will go in depth and letting you know how it is log k to the power n if you are interested. We have A, B and C, D. So we need to find some kind of a connection between A, B, C, D. Even you don't even have to understand how it is log k to the power n or logarithmic time. It just we can try to understand it through first principles itself. So we have different vectors here, and then we wanted to search for a query here. So first we need to understand how are these neighboring graphs are connected with each other. It is very intuitive that we check some kind of a measure which we already have, like this cosine similarity, Euclidean distance, or whatever. Let's take, we have this classic distance formula. So we calculate the distance between between each other, and then we form this kind of a graph here, and we can give different parameters to it to say to determine how our navigable graph should look like. Suppose we have here m as the neighbor count. I can fix the neighbor count as 3, like this example. So we can make sure that any node will have at max 3 connections with another node, and then this node will have at max 3 connections. This will have at max 3, and so on. So now here A and B is near to each other. That's why you see them connected. Out of A, B, C, D, E, F, we can at max connect to 3 neighbors because we have set the M as 3. So A can connect to 3 of the nearest neighbors, which is B and C and D here. Out of B, C, D is somewhere far away. So eventually you can see that there can be another small clusters here, another small cluster here. D can be connected to this cluster. So if you can, suppose we wanted to search something that our query vector belongs to this cluster. That is, we wanted to search something and then the result is in this cluster. We can go to this D and then directly skip to this cluster so that we can totally avoid searching through the other elements of the cluster. This is the advantage of having something like a navigable graph, so that you can skip a lot of elements and go to a cluster which is more relevant to you and then eventually search out of it. So this is a simple graph traversal. Like how do you do it? If you have interest in data structuration algorithms and if you have practiced graph algorithm, it is nothing but you do some kind of an BFS here, which is instead of breadth first search, it is best fit search. So you can use a priority queue and then keep track of it, do all sort of things, and then move to the cluster you wanted to. Now let's come to the important part: how all of these are linked with each other. Now this comes to our main hero of the day. Why do we need a hierarchy here? Just like how I explained Skiplist, it takes from the idea of Skiplist. Instead of you going and navigating through all the places in your small world, if you have a distilled version of it at a higher layer, you can directly find the relevant clusters from the above layer and then easily access it. Instead of going through all the numbers, you can get the result in logarithmic time here. So let's just understand with some. So there are different parameters which you need to understand for understanding hierarchical navigable small worlds. First is the neighboring count, which we I think it is clear by now. It's just how many neighbors a node can have. It is nothing but the number of edges a node can possess. Suppose this so if we set n is equal to 3, it can have maximum 3 edges attached to it. And then we have something called an layer multiplier. So we need to like in the Skiplist example I told you, right, we do a time cost as a function, but here we need to have some kind of a function to determine which layer the node goes here. That is our layer multiplier. Usually we do an e to the power minus level by ml and so on. So just understand that we say put it to some function and then that function returns us the layer to it. Then we have one parameter called EF construction. First we need to when you put a data inside Pinecone, it first needs to create this navigable hierarchical navigable small world, right? So to build this, we use something called an EF construction, which is just some value. Like assume EF construction is 5. I will while I go through an exam, while we go through an example, tell you where it is all used, and then we have something called an EF alone, which is called exploration factor doing search, which let me assume it is 3 for this example. So now like everything might sound very gibberish, but let's try to understand how this algorithm works. So first we need to create this hierarchical navigable small world, because when you put a vector into this database, you need to first create this graph so that you can eventually search or insert or do whatever. So how do we first create this? Compare our skip list and this so that it will be easier to understand. This is nothing but our level 0, level 1, level 2. So what level 0 will have? Level 0 will have the highest density because it has almost all the numbers, all the vectors in it. And the level 1 will be a distilled version of it. And level 2 is another distilled version of it. How do you create the levels? There we did a time cost. Here we will use the layer multiplier, some kind of a function, exponent logarithmic function, which will determine that whether the element will go to that layer, or sorry, whether the vector will go to that layer or not. Suppose you have a value 1 in skip list, that value might exist in the upper the layer above. The value might or might not exist in the layer above. But if a value exists in one higher layer, it will definitely exist in the lower layer and the layer below, because it is eventually created from level 0 to higher level, right? So the same works here. What does that mean? That means the lowest level will have higher density in the sense higher number of values there, and then the layer above will have lesser density and so on. Why this layer should have highest density? If it has the highest density, that means it will have all kinds of a cluster like this. You can see it has a lot of clusters in it, so that you can find more accurate results to it. So we'll take one query vector here. First, we enter from the highest level. Why do we enter from the highest level? Because if we can find some relevance in the highest level, from there we can split across. Suppose take this diagram. You have two nodes here. Assume there is two nodes here. Suppose you find some higher relevance with this node, then you can completely skip the nodes below here and concentrate on its layer below and find those clusters instead of just going through everything here. So now, because of starting from the higher layer, you are eventually skipping most of the section here, right? So that you are able to take a very substructure or small world here, and then taking the highest relevance instead of going through all combinations. First, let's see how the insertion works. Let's insert a node B here. First, we need to determine the level. So using our multiplier layer, it just gives you some level here, which is a randomized level. It doesn't have to be some exact level. Suppose we have some kind of a function which determines our level. Here it says e power minus level of this multiplier and so on. Assume some kind of a function which gives us the level here. So it says B should be at level 3. Eventually we need a complexity of log n. So it just needs to form something like a pyramid where the lowest layer has the highest density, and then the number of nodes keep decreasing, and as well as we should make sure that the level doesn't exist the logarithmic of the number of elements, because it breaks the whole purpose of creating this hierarchical navigable small world, which is the main use. The main use of creating this itself is to get a logarithmic complexity here. So first we start, suppose we need to insert B, and our layer multiplier, or the function which helps us to identify or generate a random layer, says us to insert a certain layer. Suppose it says us to insert at layer 3. So now we don't even have a layer 3. So we insert that at layer 3. And then we insert at layer through. So because when we insert something at the topmost layer, every layer below that should have the same value. They have that value, right? That's how our skip list works. Because in skip list we fill from low to high, and here we are trying to fill from higher to lower. This is where our EF construction helps us. So this EF construction is the exploration factor during build. This EF construction is very important here, because when you wanted to insert a new node inside this cluster, we need to make sure that we create this right kind of links. So assume this, we create something called layer 3, because B is being inserted at layer 3. Since there is nothing in layer 3, we directly insert B here. But now we wanted to insert at layer 2. How do we insert at layer 2? To insert at layer 2, we must again find the distance here, because we are using Euclidean distance as our measure here. we find the distance between this node. We find the distance between this node, and we take this and we have distance a1 and distance a2. This is where EF construction metrics helps a lot. So here we have assumed the EF construction is phi. What does it mean? We'll take an analogy. Suppose you wanted to build a road or connect a road. There are like 10 different roads which already exist. Either you can go to every number out here and check and find its distance or find the best measure, and that is one way. The other way is, this is exhaustively searching. Suppose you have like 1 lakh roads, 1 lakh possibility roads, you can go link with it. What you can do is, you can either go to every single one, take a measure out of it, and then find the shortest one out of all or the best one out of all, and then link with it. This is one way. Now what you are doing is, you are exhaustively searching through all the roads. Instead, what you say is, you are given an EF construction. That is, they are saying that you have an EF construction of 5. What does it means is, it is enough for you to check 5 nodes along with you and then take the best. Why do we do this? We do this because we don't have to exhaustively search through the result. So you can understand what problem it causes, right? We have a low EF construction. Suppose for a 1 lakh road, if your EF construction is 5, you literally not seeing remaining roads there, which will definitely have a better, definitely have a better path, which you can choose as part of the M. But if it is if the M is extremely high, like 1 lakh, you are doing a more number of search, so your algorithm's time complexity will increase because you are doing an exhaustive search. So you need to find an intermediate balance between the number which you give. It is not as it shouldn't be as low. In some case, it can be lower as well, and it can be extremely high as well. It depends on the use case. I have an authority to go and search for 5 different nodes and take the best M node and connect with the best M node. So I am here we have only 2 nodes. So I am checking with the node 1 and I am checking with the node 2, which is less than 5. So I have 2 distance here, A1 and A2. And then out of it, I can connect since the M is also 3 here. Assume M is 3 here. So each node can connect with 3 different nodes. So I have no problem. I can take the best 2 nodes out of this because I have only A1 and A2. Suppose I have A3, A4, A5 or 5 different nodes. I will always take the best result out of it through a priority queue. I use a priority queue with A1 and A2. So I will move from A1. I'll take the shortest distance, whichever has the shortest value. I will calculate. I will have it through priority queue. Suppose A1, A2, whichever is the smallest is always in the front. Which is nothing but a min heap. I maintain a min heap. Whichever is the smallest one is in the front. So with that help, I will slide into this layer. This and this, I will just store the pointer values of the, because since both have the same value, I can always store L2 A pointer, L1 same A pointer. So since this has the lowest value, I can find this A in the next pair and go to this pointer. So I have reached this pointer. Assume our EF construct is 2. It doesn't change. Initially, you set one EF construct, it works all over the place. I'm taking a smaller number to demonstrate here. Assume EF construct is 2 and you reach this node here. You are at the starting point. So now you have, assume there is another node here as well. So this node has been connected to 3 nodes here. But since your EF construct is 2, you can only explore 2 nodes out of the 3 nodes. Some random 2 nodes out of the 3 nodes first. And then after exploring the 2 nodes, you can take the best M nodes out of it and then connect it with each other. So I'll have distance D1. I'll have distance D2. Since I can explore only D1 and D2, I'll take the and M is 3. I can link this newer node to both this one and that one, and so on. This is how you insert a node in hierarchical navigable small world. And the next important thing, the most important thing is the moment you create all the nodes and this whole tree structure is ready. The next thing which you need to do is search through it and then identify the node. So we have inserted some value. Now we need to search a value. This is very similar to how we do it in Skiplist. But this time we use some value called EF, which is exploratory factor. Just like how you used an EF construction to determine what are all the nodes you will see through to construct the new node or insert the new node. You use this EF value to make sure that what are the nodes you will search through it. That's it. Very simple. So first you started at the entry point. You go to a point A. You have some Q here, value Q, that is some query vector here, and then you see this is very similar to Q, and then you always have this Q value here, and then you go to the second layer, you find the shortest distance, and how many nodes you will explore this time. You will explore at max EF number of nodes. This is the same analogy which I explained with the roads there. So after since if EF is 2, I'll at max explore 2 nodes, and then I will from here I've reached here, and out of these 2, this is the smallest value. I will go here. From here I will move here. I will move here, and then I can go. I can search the other nodes, or if I see the nodes are the values of the nodes are extremely high when come. How do you calculate it? I have a priority queue here, so I add Q1, Q2, and I see both the values are extremely high. That means I will directly go to the layer below, because the more layer which we travel, we can always stop at the layer which we wanted. But the right way to do it is start from the top of the layer, go to the layer 0, because at the layer 0 you have a dense cluster. That means you can search through a lot of elements here. There is a high possibility for you to find an exact match is high, or a very similar match is very high if you go to level 0, because you have more number of nodes to check, so that the probability of finding that is very high. So you come to level 0, you do exploration until EF value. So what exactly happened here is, since this value is been not chosen, this is just a greedy algorithm search. Since this value is not chosen, you are not going to choose this whole half of it, and then you are going to just concentrate on this small word. So eventually you see, instead of searching to all the numbers, all you do is start here, come here, here, and then once you get an n number of results, you take out of it, and then return the most similar results to the for this query. So if you would have used a hierarchical navigable small world, you would have traversed to all these nodes, and you would have searched all these nodes. You would have traveled to all these nodes, and you would have searched all these nodes. Now here, because of doing this way, the time complexity becomes O of log n, because you do a logarithmic search. Because by creating this hierarchical navigable small world itself, we create it in such a way that the height doesn't exist logarithmic time, or the layer doesn't exist logarithmic time. So the search is also somewhere at the logarithmic time. I hope this video is a little bit more complex to understand, but hope you understand this video. And there are there are official blogs written about this hierarchical navigable small world, and especially Pinecone, which is a vector DB which uses this algorithm in it, has a detailed blog about this, which you can always go and check and understand it. If we take a little bit more time to figure out what I told, it will be even more simple. But I wanted to go in deep in explaining how the results are found, because I couldn't find any resource on YouTube. That's the reason I chose this topic for the day. I hope you like this video. I'll get back to you with another interesting video. Bye.